Hey guys, so here's what you're doing today. Go ahead and set up these notes. The topic for today is buoyant force, and I just put in parentheses buoyant to remind you how to pronounce it. The essential question to copy down underneath is, what is the strength of the buoyant force, or the size of the buoyant force, and how does it affect floating and sinking? Take a minute to set up your notes so you have a section to take the notes, write some questions about each section, and then answer the essential question at the bottom. Here's the first section. The definition of buoyant force is that it is an upward force pushing on an object that's in a fluid. Remember that a fluid is anything that flows. So it could be a gas or it could be a liquid. This is why hot air balloons float, because there is buoyant force that comes from the air, but there's also buoyant force that comes from any type of liquid. And that could be water or milk or soda. Anything that's in a fluid that flows from one place to another has a buoyant force. Buoyant force is a vector because it has both size and direction. Any force has both size and direction. Take a minute to pause, draw one of these pictures, and then write a question about this section. So when will an object float? An object will float if the weight due to gravity is equal to the strength of the buoyant force. So when these two forces are balanced, then the object will sit on the top of the surface of a water. It won't be shooting up into the sky. It won't be sinking down to the bottom. So we know that since it's staying in the same place, the forces are balanced. This is called positive buoyancy. And if we were to give, for example, these vectors units, we might say that the weight of the rubber ball is 10 newtons and the strength of the buoyant force is also 10 newtons, balancing each other out so the object will float on the surface of the liquid. Pause and write a question about this section. When will an object sink? An object will sink if these forces then are unbalanced, if the weight due to gravity is greater than the strength of the buoyant force, in which case we call this negative buoyancy. So if we had a steel ball or some kind of metal rock or some kind of metal object that we would say, oh, that's heavy, then it would sink if the buoyant force is less than the weight of the object due to gravity. Pause this, draw the picture, write a note about this section as well. I want to tell you a story about a Greek mathematician who lived hundreds of years ago. His name is Archimedes. The story of Archimedes goes that he discovered that there was a connection between the size of the buoyant force and the displaced water when you put an object in water. So the story goes that he was given a task from a king. The king said, hey, I want you to find out if my gold crown really is gold, but you can't cut it open at all or damage the crown in any way. So Archimedes was trying to figure out, well, what do I do with this? And then he went home and he was taking a bath. That's what this picture is. When he got into the bathtub, he realized that the water overflowed. And the amount of water that overflowed was equal to how much his body took up. So then he started thinking, if I take that displaced water and weigh it, then what does that tell me? Here's actually the real story, or according to some people, the real story of Archimedes.
When you think of Archimedes' eureka moment, you probably think of this. As it turns out, it may have been more like this. In the 3rd century BC, Hieron, king of the Sicilian city of Syracuse, chose Archimedes to supervise an engineering project of unprecedented scale. Hieron commissioned a sailing vessel 50 times bigger than a standard ancient warship. Named the Syracusia after his city, Hieron wanted to construct the largest ship ever, which was destined to be given as a present for Egypt's ruler, Ptolemy. But could a boat the size of a palace possibly float? In Archimedes' day, no one had attempted anything like this. It was like asking, can a mountain fly? King Hieron had a lot riding on that question. Hundreds of workmen were to labor for years on constructing the Syracusia out of beams of pine and fir from Mount Etna, ropes from hemp grown in Spain, and pitch from France. The top deck, on which 8 watchtowers were to stand, was to be supported not by columns, but by vast wooden images of Atlas, holding the world on his shoulders. On the ship's bow, a massive catapult would be able to fire 180-pound stone missiles. For the enjoyment of its passengers, the ship was to feature a flower-lined promenade, a sheltered swimming pool, and bathhouse with heated water, a library filled with books and statues, a temple to the goddess Aphrodite, and a gymnasium. And just to make things more difficult for Archimedes, Hieron intended to pack the vessel full of cargo. 400 tons of grain, 10,000 jars of pickled fish, 74 tons of drinking water, and 600 tons of wool. It would have carried well over 1,000 people on board, including 600 soldiers. And it housed 20 horses in separate stalls. To build something of this scale only for that to sink on its maiden voyage, well, let's just say that failure wouldn't have been a pleasant option for Archimedes. So he took on the problem. Will it sink? Perhaps he was sitting in the bathhouse one day, wondering how a heavy bathtub can float, when inspiration came to him. An object partially immersed in a fluid is buoyed up by a force equal to the weight of the fluid displaced by the object. In other words, if a 2,000-ton Syracusia displaced exactly 2,000 tons of water, it would just barely float. If it displaced 4,000 tons of water, it would float with no problem. Of course, if it only displaced 1,000 tons of water, well, Hieron wouldn't be too happy. This is the law of buoyancy, and engineers still call it Archimedes' principle. It explains why a steel supertanker can float as easily as a wooden rowboat or a bathtub. If the weight of water displaced by the vessel below the keel is equivalent to the vessel's weight, whatever is above the keel will remain afloat above the waterline. This sounds a lot like another story involving Archimedes and a bathtub, and it's possible that's because they're actually the same story, twisted by the vagaries of history. The classical story of Archimedes' Eureka and subsequent streak through the streets centers around a crown, or corona in Latin. At the core of the Syracusia story is a keel, or korone in Greek. Could one have been mixed up for the other? We may never know. On the day the Syracusia arrived in Egypt on its first and only voyage, we can only imagine how residents of Alexandria thronged the harbor to marvel at the arrival of this majestic floating castle.
So the story also goes that when Archimedes made this discovery, he was so excited that he jumped out of the bathtub and ran through the streets naked and yelled Eureka, which means I discovered it. I want you to draw this picture and take these notes and let me explain. I like this picture a lot, and I don't like this picture because it uses pounds, and we don't use pounds for metric system, but it does get the point across. You need to get in your notes that Archimedes' principle says that the buoyant force is equal to the weight of the displaced water. So let's say we had a bucket that had a spout on it. We filled the bucket all the way to the top and then put something underneath to catch the water that's going to come out. Then we took some kind of scale and hung an object from it. So this scale right here tells me the weight of this object due to gravity. The weight of this object due to gravity is apparently 7 pounds according to this scale. Well, then I put it in the water, and now the scale only reads that the object weighs 4 pounds. Well, the object didn't actually lose mass, but there is something else going on here. A buoyant force pushed up on the object, making it look like it was less weight. So it went from 7 pounds to 4 pounds. That gives me a really big clue as to how much buoyant force is pushing up on it. It must be 3 pounds. 7 minus 4 is 3 pounds. Well, according to Archimedes' principle, then, when you put an object in the water, it displaces water. And if you were to catch that water and weigh that displaced water, the weight of that water will tell you the size of the buoyant force. If this water weight were to weigh 3 pounds, that will tell you the size of the buoyant force. In this case, the object would sink because the weight of the object due to gravity is still greater than the buoyant force. Make sure you get this part in your notes. go and write a question about Archimedes' principle, go back through your notes, highlight important things, and then answer the essential question at the bottom.